everyone. Um, just a minute. So, yes. Okay, can you hear me?
Yes, we can see your screen.
Yes.
Okay, thank you. Okay, thank you very much, Zainab, for the presentation. And I will carry on from here. My name is Mohammed. I'm from Sudan also. So my domain knowledge or my main background in information, I graduated from control department where I acquired knowledge in automation, specifically in PLC, programmable logic controllers and SCADA systems, supervisory control and data acquisition. So after that, in my master's degree study, I decided to shift from automation to data science or machine learning in general. So from here, we're going to carry on with training the model. So we have seen how to collect, like how to define the problem, how to collect the data, how to prepare it and process it before feeding it to any kind of machine learning algorithms or model. So you may say that this is the this is the most important section in or part in machine learning, but it isn't. And like you as them say that you're gonna spend most of the time preparing the data and processing it before feeding it into machine learning models. So here, like in general, the webinar is designed to provide an overview information about how how the journey of machine learning looks like, and it's not intended to provide any like practical information or coding to show you how it is actually, but instead giving you the intuition of how machine learning journey can look like. So. But I will try to provide to give you some information or provide some kind of practical parts to show you how each section of the machine learning journey or life cycle looks like. So starting from here, model time, like training the model. So before diving into machine learning algorithms types or models, we should first differentiate between the classical programming and machine learning algorithms, because some people get confused by the analogies of classical programming and machine learning algorithms as they use in coding to solve problems. But in classical programming, or provides the data, or provides the rules, and we tell the computer how it is done. Like, for example, let's say that we're processing information, like for example, let's say that we're calculating the average score of a class of students in math course. So we provide all the scores which represent the data here, and we provide the formula how the average is calculated, which presents the rules. So, and after that, we run the code, and we have the answers. So we know the rules, we have the data, but we need the answers. Unlike in the machine learning models or algorithms, we have data and we have the answers, but in this situation we don't have, like, I'm just giving an example, but we may not have even the answers in specific situations or conditions. But for here, let's assume that we have data and we have the answers, but we don't know the rules. For example, we want to differentiate. Like, let's say that we want to build a model that differentiate between cats and dogs, well, by looking into images. Like our main data are images. We provide the images as our data, and we label each image with its class. For example, let's say that we have dogs and cats, just dogs and cats. We provide images of dogs and cats with associated label with each image to tell the machine which one is cat and which one is dog. So what does the machine learning algorithm do? It tries to figure out the underlying pattern between like that differentiate cats from dogs. Like it's gonna trying to figure out what makes a dog and what makes a cat, and try to find like some features to differentiate between them. And these features, for example, let's say that the dogs may look bigger in size when we compare them with cats. This can be a rule. Like if we have, for example, let's say we have scold of 5 meters, like let's say 2 meters in tall. If the animal, like whether it is cat or dog, is it's high, like its size is higher than 2 meters, that we're gonna classify it as dog. If it's less, we're gonna classify it as cat. So here we're gonna get the rules that we can use to differentiate between two categories, two classes. And this is just one example of machine learning algorithms like to solve problems. So we have a lot of problems. And the problem that I have discussed is called classification, in which the machine learning algorithm tries to figure out the features that can be used to differentiate between different classes or categories. So here's the main difference, or the key difference between classical programming and machine learning. And because of that, because of these figures, like we have here the algorithm, will provide the data and the answers. Sometimes we may not have rules that we can understand, as we can see later on this presentation. So we have kind of rules that human brain cannot understand, but the machine can. And we fell into a problem of interpretability. Like we have decisions made by a machine, but we cannot trust because we don't know how exactly it is, like this decision has been made. So this is another problem called black box, which the black box represent the rules that we don't know how it is used, or what is the rules that used to make this decision. So let's go to another part where we learn how the machine learns. So let's imagine that you are trying to teach your little brother how to differentiate between cats and dogs. So obviously you start by showing him some pictures of dogs and cats, and you keep telling him that this is the cat, this is the dog, this is the cat, this is the dog. So he will have the intuition of how all the dog looks like and how the cat looks like. After you showing him a bunch of photos or pictures of cats and dogs, you would also test him to see if he learned it or not. So you start to show him some images that you haven't shown before to test him. And he may make mistakes. So these mistakes, you're gonna correct him and try to optimize or to improve his understanding of how dog looks like and how cat looks like. And you try this many times. Like you provide pictures of cats and dogs. You test him to see his mistakes, and according to these mistakes, you provide some other pictures that can simulate or like makes him differentiate between cats and dogs, specifically on the ones that he made mistakes on. So you keep doing that until you get into a point that he is correctly identifying cats and dogs, not 100%, but in a level that is considered satisfactory for you. So it is the same situation. Machine learning, you provide data, the algorithm, like we have, like we're gonna see. We're gonna see many types of algorithms that can be exploited for specific problems. But in general, you provide data to the machine learning algorithm, and instead of making mistakes, we calculate something called loss function, where we find the difference between the predicted class and the actual one. So we measure the error. So according to that, we fix problem, trying to fix a problem. I don't want to go deep into details like weights and it's like a lot of information, like as ingredient descent and this as such, and this kind of optimization algorithms. But we have kind of optimization algorithm, and it is job to try to fix the problem, like to fix the place where the problem is generated from. Like let's say that let's make it simple. Let's say that we want to find the number that if we multiply it with 2, the result is going to be 3. It's going to be 6, which is 3. But we ended up having 2 multiplied by 2.5. And the result is 5 instead of 6. So we have difference, or we have error of 1, like 1 unit. So we know that the error is not big. So we have to fix the 2.5 to another number higher. So we pick up like even the addition we're gonna make on 2.5 is calculated using the optimization algorithms. Like we have different ones, but in general, it calculates the error and try to fix it by adding term or subtracting term. Like if instead of multiplying this in the first time by 2.5, we may multiply it by 4 and ending up having 8 instead of 6. So we like our difference here is -2. So we know that we multiplied our number, which is 2, by higher one. So we have to subtract it, like we have to decrease it into a level that we can get like at least less error, instead of like even if we didn't get the exact number, we're gonna ending having less error than that time. So we keep doing that iteration. We iterate over all the process, all the steps again, which is in machine learning terms we call it epochs, which the error is calculated and optimized many times until we reach into a point that we can decide it is good for us, so we can stop training. So I hope that was clear. So and now we know how machine learning works and how the computer learns from data to provide some answers for us. Let's explain an example of how machine learning algorithms are utilized in real world applications, like Netflix here. Netflix uses machine learning algorithms to increase profits by engaging customers or clients, or even like retain them again. So how that it is done? Basically, when we log in into Netflix, we have an account. So under that account, when we log in, all the information or all the events or the clicks we do inside the app is recorded. And the movies we're watching, the likes or the rating we are giving, the navigation, like the scrolling we are doing, and even if we stop for a second to read description or to read or to see thumbnails of some movies, that is recorded too, to see your behavior, how you behave inside the app, so they can get insights about their users. So they utilize your viewing history, like the movies you're watching, the rating you're giving, and also like the scrolling you're doing inside the app to provide you with some recommendations. For example, let's say that you watch Avengers movie, so that is recorded. Their goal is to give you recommended personalized content. Like they want you to be engaged in their application, to spend more time, to subscribe, of course, and pay money and like make their profits high. So they are trying to make you more engaged in their application by recommending you movies that you may watch if you watch specific movies. So let's say that we have two users, user A and user B. User A watched Avengers movie, and after Avengers movie, he watched let's say that Spider-Man after Avengers. So they getting the intuition. If someone watched Avengers, the next movie that he will be interested in is Spider-Man, because another user has the same taste, watching that movie, and the next movie is Spider-Man. So we're gonna recommend this movie to that one because they have similar profiles. And that is not that simple because they're using different kind of information. For example, the metadata associated with each movie, like the type of the movie, its time, the actors, the theme, a lot of information with metadata that associated with each one, and also the navigation you're doing, and how long you spend time, like how long time you spend inside that movie, like. And when you watch that movie, a lot of information are collected without you knowing that, and used for recommendation for making recommendation for other people who may have the same profile as you. So they make them more engaged in their profile, in their application, and maintain their subscription for as long as possible. So they're using for recommendations for providing recommendations. They're using collaborative filtering, which is a kind of machine learning categorized under recommendation systems. So, and also they're using NLP as well. So according to the resource that I provided under here, they're saying that 80% of the engagement in Netflix is driven by recommendations they're using. So over $1 billion is generated just by using recommendation systems in Netflix. So you can imagine how many you can generate using using machine learning algorithms in businesses. So uh, this is just one example. There are a lot of examples out there, like Amazon, Apple TV, and other. We have also ChatGPT, we have Box, and a lot of AI-based applications. So here are the categories of machine learning. We have supervised learning, we have unsupervised learning, we have semi-supervised learning, and also we have reinforcement learning. Okay, sorry, I'll try to go more faster because we have limited time. But next time, maybe I will provide more information in each part. So basically, for the supervised learning, we have, as I explained before, the same example that we have data, and each type of this data is associated with label to tell the machine this is dog, this is cow, this is camel, this is elephant. So we're providing labels with that. So we're telling the machine that this is cow, this is dog, and this is camel. So it's called supervised because as a user or the programmer or the developer provides data with labels. So the algorithm finds the differences or the features that can be used to differentiate between these types, processing it, and providing the output. So when we provide other data that the machine learning algorithm has not seen before, it can provide the correct results. So on the other hand, we have unsupervised learning. Unlike supervised learning, we don't provide any kind of labels. We don't tell the machine this is cow, this is dog, and this is a camel, for example. We just provide the data, and the machine learning algorithm will try to figure out which, to find similar features that, group some kind of label pictures together or data together. For example, if the machine learning looks into elephant, like many different kind of elephant images, gonna find that the similar feature between all the images and categorize them just into one category. So for supervised learning, it's combined both the supervised learning and unsupervised learning. So we have portion of the data that is labeled and the rest of it is not labeled. And the machine learning algorithm will try to figure out which category, which image is belonging to which category. So this is used when labeling data is time consuming and expensive. So we have portion of data is portion of data is labeled and the rest of it is not is unlabeled. So for reinforcement learning, we have an agent or machine like device or whatever, and it's navigate in the environment that has not seen before. And according to the actions that are being made in that environment, a reward is given. So when large reward is given, so that means the action is good or it's correct. And when less reward is given or even penalty is given, the action is not right. So it's won't be done again in that position in the environment. So until we reach into the point that we have a satisfactory result. So here are the categories of machine learning: supervised learning, unsupervised learning, and reinforcement learning, and the problems that can solve. For example, for supervised learning, we have classification and regression. And for each one, we have a bunch of algorithms that can be used to solve that kind of problem. So we have a lot of information here. I won't be navigating them right now, but here is an intuition of machine learning classes like categories and their associated problems and algorithms. So in the same situation here, for each problem, we use a specific kind of algorithms for each specific problem. We have a lot of options that can be used according to that problem. So you define the problem and you see which one of these problems which one of these categories a problem is divided. So according to that, you're going to choose which algorithm is suitable for that problem. For example, I'll just give one example. Let's say that we have a problem where you have to predict the price of department according to their size and location. So you are trying to predict a continuous value. In this situation, you may use it's called regression problem. So when you're trying to predict this value or continuous target in your problem, like predicting price of a house or department according to based on its location and size. So it is a regression problem. After you identify a problem, you are going to find the algorithms that can solve regression problems, like linear regression, for example. You can use linear regression to predict price of a house based on its location and etc. So according to the problem that you have it at hand, you can choose a specific algorithm that can solve it. And also, as you have many algorithms that under that kind of problem, you can try them and make a comparison to see which one performs better in your situation. So after we train the model, how are we gonna evaluate the performance? How are we gonna know that it performs good? And this is the kind of performance we need or we are targeting. So we have a lot of evaluating metrics that can be used to evaluate the performance of a model according to the problem that you're trying to solve, according to the data that you have at hand. So instead of evaluating the problem, you may fold out some data far from the training data. So let's say that you have 100. Let's say that we have 200 images data. 100 is 100 images representing cats and 100 images representing dogs. So we have to train the model on a portion of that data and testing the model using data that the model hasn't been seen before. So have not seen before. So we split the data into training and testing data, and the standard or like you are free to use like the percentage of data that can be provided into like as training set or testing set or validation set. You are free to choose, but the standard is 70% for training, 15% for testing, and 15% for validation. And if you have a small portion of data that you cannot split this way, you can use a cross-validation method in which you fold out one portion of the data and train the model on the other portions and test it in that portion. For example, for the first, let's say that for the first split one here, we have the data. We split it into 5 portions. We use 4 of them for training, and we're testing the model using the one that we folded out before. And we do that again, but this time instead of using this portion for testing, we're using the second one for testing and the others for training. And we keep doing that for a specific number of splits. Like if we have 5 splits, and then we're gonna do that 5 times. And And in that situation, when we have a small portion of data at hand, we should use cross-validation. So we make sure that the data, like the model results, are is generalizable and can perform well on unseen data. So that is all about how to split the data into training and testing, like I said. And also we have validation here, but I will skip that for now. But maybe we're gonna discuss it in more details later on other papers. So we have after we train our model, like after we split the data and train our model, we want to see how the model perform. So for classification problems, let's say that we have two different categories here, and we're trying to separate them, or to make a line that separates two classes as much as possible. For underfitting, we have three terms: underfitting, overfitting, and trade-off situation. For underfitting, the line is not fitting the data very good. Like, it cannot separate the blue dots from the origin, the orange ones very, very, very good. So we can say that the model is categorized under underfitting. So we need to solve that problem, which we have specific steps and methods that can be used to solve underfitting problems. So when the model lets the data very much in a way that can separate each one of it from each other, like the blue dots are perfectly separated from the original from the orange dots here. It's called overfitting. It's responsible in training, but when we provide unseen data, the model is going to perform bad because the model memorized the features of the data provided to it. So instead of making generalization and finding features that can be used to differentiate between these different dots, it memorized the whole features. So in a way that cannot generalize the result on unseen data. The same situation goes to regression problem. As I said before, classification is identifying different categories from each other, and regression is trying to predict a continuous value predict a continuous value, as the example that I have given before, in which, like, you predict the price of a department according to the size and location. So also we have a lot of performance evaluation metrics we can use, like accuracy, precision, recall, and F1 score. And also we have conversion matrix. Conversion matrix can provide a lot of information, like detailed information about which class has been classified as which class. Like, for example, here we have true positive, false negative, false negative, false positive, and true negative. So I don't want to dive into details, but when we use conversion matrix, we're gonna have the intuition that this class is classified correctly, like how many images have been classified correctly, and how many images have been classified to another class. So, for example, let's say that we want to classify to make classification, like to classify human activity, like, for example, walking, running, laying, or just climbing up the stairs. So when we make the classification, that, like, when we evaluate the performance, we can see that because the the running and and working data can like can like can be looked similar to each other. That's why the model can be confused between which one is running or which one is the data belongs to running class or belongs uh, to working class. So now we pick the model. We are satisfied with the results at hand. The next one is to testing it on unseen data, like make predictions or decisions. So according to the category that we're working on, like either it is supervised learning, unsupervised learning, reinforcement learning, or semi-supervised learning, there are specific kind of uh, predictions that can be made. For example, in healthcare, if we provide images of, like as Zainab said before, of X-rays into our models to identify which kind of illness that the patient may have, the prediction be the same way. We provide an image after the model is trained. We provide an image, and the result and the expected results are gonna be one of the illnesses that we defined before. And also, if we trying to predict, if we're trying to predict a price of an apartment according to its size and location, the expected results are going to be the price of that apartment with that specifications. Let me show you just an example of that. Sorry, that really takes a long time. It's better to show you. Okay, let me present. Okay, I have built a model to just show you uh, how the prediction can be made when. Sorry. How a prediction can be made when we use it for price prediction. I should sorry for that, but this thing. So this is an example of how prediction are made in like integration problems. Let's say that we trained our model to predict the price of a house or houses uh, according to their size and number of bedrooms. So when we enter, for example, 200 feet, feet squares, and the bedrooms that we have is three. So predicted price is $27,000. So here there are a lot of considerations you may have. Like a lot of considerations you may uh, mm, uh, like mm, um, before we do that, like example, the data the data you trained our model your model in, but from which location? Is it from, for example, Istanbul? Is it from New York? Is it from Washington D.C.? Because the prices are very different according to that location. So, because in this situation, in this model, which it just predicts the price of a house according to its size and a number of bedrooms, and not and it's not considering any kind of location. So it is just built built to serve a specific city or a specific location. So that's why it's not considering as it is indicators or variable. So that's an example of how predictions are made. So after we do that, like I have shown you the deployment part, but I should have shown you how how the model looks like when you train it actually using codes. So let me show you just one of my existing example. So in this example, we train our model using cat and dog to see to predict or to classify cats and dogs. So provide a lot of images representing cats and dogs with a lot of pre-processing, data augmentation, a lot of stuff that I won't be discussing here. Maybe discuss maybe we discuss another time on another webinar. But I will show you how the training looks like when you train your model. For example, here using CNN or convolutional networks, and this is a training steps, as I have explained before. There are a lot of iterations to try to calculate the loss, and the algorithm's job is to decrease that loss, and decrease the loss and increase the accuracy. As you can see here, we started with the loss equal to 2.96, and as we progress. As the training progresses here, we can see that the loss is decreasing. The loss is decreasing, and also the accuracy is increasing. So we're trying to increase the accuracy and decreasing the loss. So until we reach to satisfactory results that we can. After that, we can start the training. So as we can see here, as I showed you before, that the overfitting term, the overfitting and underfitting terms. As you can see here, this is just right because the training. I didn't show. I should have shown you how the accuracy and loss function look like when you train a model, and how to differentiate if it is overfitting or underfitting. Let's just try here. So if we look into here an example of how the accuracy will look like if your model is performing and overfitting. Like you can see here, the training accuracy is high, but the validation accuracy is very low. And also here you can see the opposite with the loss. When the loss of the training is decreasing, the loss of validation is increasing. So when your model is performing like this, like the training accuracy and the validation accuracy are neck to neck, so the model performance. So this is an example of how predictions are made. The predictions are made exist when you use it exist, like you model is, and you use mesh of that model called provide provide this stuff as is this the image is stored in X. So we make the classy, but if we more than this format, no one can use it. Like I'm normal users, so you have to be bit to model in this way, like in code way. So in in order to make it accessible for each one, and 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 um, and everyone can use it without any problems, you have to design a user interface, and have to put your model so that to serve that that application or that user interface. So as I showed you just a minute ago, I designed this one using HTML, CSS, and a little bit of JavaScript. And behind this user interface or this website, I'm the setting or power the prediction process after the information are sent to the model in the background to process it and provide the prediction into a user interface. This is exactly what deployment is. Like deployment is putting your model into live and make it accessible for everyone to reach, and using a bunch of languages, of course, HTML, CSS, and JavaScript, and putting it into so the server will 24/7, and you may associate your server ID with a domain name, or just keep it as ID address and provide it, but it's not good to provide ID. So let me continue. Sorry. Okay, yeah. So in deployment, we have like different scenarios that we can deploy a model on. For example, we can use APIs. In APIs, it is application. It is application interface where you provide endpoints from your model, so everyone can use in their application. For example, we have GPT right now, which everyone can use directly without any problem. But if you want to utilize ChatGPT, for example, as Apple did in their latest iOS VPN, they're using APIs from ChatGPT to power their large language models to provide some features like, for example, writing professional way, or make concise concise your text. So they're using APIs. The model is not theirs. They're using ChatGPT model, but with APIs, which the requests are sent to ChatGPT, and then the response is sent back to your device again. So in this situation, you deploy a model and provide endpoints, so everyone can use your application in their application, or you can deploy it in both, where you can provide real-time, for example, real-time predictions for let's give an example of predicting the price of a house according to its size, location, and other indicators that are changing in real time, like policy, policy decision, or other decisions. Also, you can use it to automate your work. So instead of having this you can use machine learning and deploy it in models to make it to automate. So you don't to automate and do the basic tasking there. So have a lot of options. Model. I can show you dashboard also, which I have done before. Dashboard. So it's the dashboard that provide insights about some specific area of the world, and there are a lot of reviews and this review are classified into compliments and complaints. So the model can identify or can predict the number of complaints that could be in the specific type of the area, and on the other side also the complement. So this is an example for that, and I will show you an example for API also, a little bit faster. So before doing that, I have built an image, and the model at website will determine if uploaded image is cat or dog. So let's get live. And my internet connection is not so good, but I think it's letting me use my data.
Sorry, Al-Fateh.
So as you can see here, you can use, like, I will provide here in the chat the link, so you can use it and upload your image to see the results. From my side here, I will upload an image to see if it is cat or dog. So let's see, I have a cat here, and I will predict. So this is a cat and correctly classified. You can try that on your own. And this is the example of deployment. I trained a model, and to make it accessible for everyone, I make it a base web application. And this web-based application have interface, and behind that interface, I provided my model to serve that. So, and also I deployed it in a production environment so everyone can reach it. It's not just deployed. It's not deployed on my machine, like it's not deployed on local machine. It's deployed in the server, so you can try it out as well. So this is another way of deploying your model. Another one also is using APIs, as I explained before. So I built an API so everyone can use it in their application. So let's say that you want to count the number of cats and dogs that entering your building. So instead of building that building a new model from scratch again and training it, finding your data, clean it, and train your model, evaluate it, and do a lot of stuff. Instead of that, you can just use my model using an API. So I built an API, and I didn't provide any kind of documentation, but in the sake of this webinar, I just provide a simple one to show you how deploying your model and providing API will look like. So here I provided an API, the same URL, but I provided a extension of API. So when you use that and you send your image to this URL, the results will be provided in this format, in the JSON format, the class and the type of that image that you have sent before. So you can use that in your code here. For example, I imported, I don't want to go to the specifics, but here I have two images. I have cat and dog. First of all, I will send the cat here, cat.png as written here. I will send it to the model, and the model will classify it and send the results again. When I run it, I get the results. It's cat. I can use that information in my code for other purposes. So when I write here, for example, dog.gbag, dog.gbag, gbg, sorry, and send it, you can see here the results is dog. So here is a simple format or simple representation of API in deployment. So there are a lot of considerations you have to take into attention when you deploy making a deployment for your model. The maintenance, you have to update the dependencies and the version models. By dependencies here, I mean the packages that you have used when you deploy your model in a specific time, which dependencies can be updated and providing more features. And also you have to monitor and track your performance. Like you have to monitor and track the performance of your model as the data can drift and system health also can be decreased. So you have to monitor your deployment environments. Also, you have to retrain the model and use shadow testing or semi releases. So I mean here by retraining, you can see here when you train your model, after you make the deployment and you put you take these considerations into account, the maintenance, the monitoring, and also the updating. And this is like the machine learning lifecycle is not done, and it's always repeated. And there are a lot of work you have to do after the deployment. Like the work is not done by doing like after you do the deployment. So you do that again. Like the data is changing, so you have to take into consideration the new data generated. For example, let's say that you are trying to make customer retention, and you collecting data, you collecting customer behaviors data. Customer behaviors data can change over time, so you have to make sure that you update your data by the time. So, and also use that data to retrain your model, so the model will be able to identify new trends, new customer behaviors to provide you with the right decision and right insights. And also you have to evaluate again your model after you retrain it, and also you have to deploy it again, and also make the loop runs again. So let's say that we have data over here, we train our model and we got accuracy of 91%, but by the time goes, the data are changing. As an example, let's take customer behaviors. Customer behaviors can change over time and be trendy according to what is going on the world. So customer behaviors can change, and we have a lot of situations that can affect customer behavior, like the economic situation and policies and a lot of things. But as the data changes, there are a lot of squeakiness in the data. If we don't retrain our model, the accuracy may be degrading over time. So here an example of like showing if the model is retrained again over time, and when it's not trained at all again, retrained at all again, it's gonna end up having the accuracy decreased. So here is the loop of how the machine learning it's not done, and it's in the loop, closed loop, and just repeating itself again, as it's called ML ops. So we have seen the project cycle of machine learning, the steps that we have to go through, from defining the problem, preparing the data, processing it, feeding it into the model, training it, evaluating the model, and make the deployment, and also continuously monitoring the results and retrain the model again. And we have seen that how model iteration and